Hello everyone. So today we are going to start a new topic, which is underwater wireless optical communication channel modeling. In the last few classes we have understood about indoor channel modeling and outdoor channel modeling. So today we'll be discussing about underwater wireless optical communication channel modeling. So underwater communication is basically exchanging information between two devices which are submerged in the water. Also communication from underwater device to shore, and from there it is connected to terrestrial network or satellite network. It has become very important area because scientists, they want to explore the ocean, do some scientific research, and some environmental monitoring, etc. And also, if you see 6G standards, it basically says that we should be able to integrate the satellite, the terrestrial network with underwater network. So basically, we are looking towards an integrated network which will combine underwater, terrestrial network, and space network. So there is a growing interest in the area of underwater communication, and also there is a requirement of high speed, low latency, and reliable communication. So far, scientists have used acoustic waves and RF also as the communication medium for communicating between two devices which are submerged in water. So these are some of the applications of underwater communication. As you see in this diagram, the red lines are either RF link or free space optics link or optical wireless link, and the sky blue line is actually communication using either optical communication or acoustic link. So you see here there are a lot of sensors on the seabed. They communicate with remote operating vehicles. They are like robotic equipment which are submerged into water, and they interact among themselves as well. They communicate with submarine, and if there is some obstacle, then the light, or whether it is acoustic or optical, is reflected from the surface of the water and reaches another sensor node or another remote operating vehicle. And these remote operating vehicles communicate with the ship which are on the surface, or the communication buoy which is again on the surface, and from here it is connected to offshore terrestrial network or satellite network. So this is overall picture of underwater communication network getting integrated with terrestrial and satellite network. So as I mentioned, there can be three possibilities. Either you communicate using optical or acoustic or free space optics. So there are three options available to us, and these sensor nodes which are there at the bed of the sea or somewhere in the middle, they can be static nodes. They can also be a mobile node, and they can have different configurations: 1D, 2D, 3D. 1D is basically they are lying on the bed of the sea. 2D can be at different heights, and 3D basically covers a volume kind of thing, or in a small volume or within the sea. So all configurations are possible in underwater. So this is a comparison slide between acoustic, RF and optical communication. So these are the three UWC technology, underwater communication technologies. So if you see the acoustic, the benefit is that this is so far, this is the main technology which is used for communication in underwater. And it can give, the plus point is that it can give a long distance range or long range of communication of the order of 20 kilometers. The limitations are, since it is acoustic, the transmission rate is very, very low, which is of the order of kilobits per second. There may be a requirement of high data rate. So this may not be an appropriate technology for a high data rate transmission. And because it is acoustic, there is severe communication latency. The latency is of the order of seconds, whereas sometimes there are applications which require latency of milliseconds or few tenths of milliseconds. So this gives seconds. And the equipment which are used in acoustic, they are bulky, costly, and they consume a lot of power. And these acoustic waves, it has been seen that they are harmful to some marine life. So it is not a proper technology for use of communication inside the sea. On the other hand, the RF technology is a relatively smooth transition to cross air-water boundaries. So if you are communicating from outside to a device which is submerged in water, there is a smooth transition. So this is the benefit here. And RF is also more tolerant to turbulence and turbidity. So as ocean, there's a lot of turbulence sometimes, so it is more tolerant to turbulence. And since it is, the waves are not very directional, so we don't require a pointing arrangement or alignment of transmitter and receiver. Strict alignment of transmitter and receiver is not required. And one can achieve data rate of the order of 100 megabits, and the distance is not very large. So for a close distance, we can achieve a data rate of 100 megabits per second. The range is very small in RF because the attenuation of RF in water is very high. And again, the devices used for transceivers in RF communications are bulky, costly, and they consume a lot of energy. If you see the optical, you can have ultra high data rate transmission of the order of gigabits per second. Using optical transmitters and optical receivers, one can get a communication speed of gigabits per second. And this is immune to transmission latency. The latency is very, very less in this case. And these are very small transceivers, so they are low cost and they require small volume or small area transceivers. The limitations are that they cannot cross the water-air boundary. So the communication has to be with some structure on the surface, could be a buoy or some submarine, and then from there you communicate to the outside network. So they cannot cross the water-air boundary. Optical waves suffer severe absorption and scattering loss inside the water that we will discuss in detail subsequently. And it gives a moderate link range of the order of few tenths of meter or about 100 meters or 150 meters. So that is the kind of distance you achieve. So sometimes, combination of these technologies can meet your application requirements. So it is not that, optical will replace acoustic and RF. In some applications, probably acoustic could be a good solution. In some applications, RF could be a good solution, or a mixture of acoustic and RF could be a good solution. So basically, these are all possibilities we have for communicating with different devices which are inside the water. So let us now understand how the optical beam propagates in underwater. So as you know that water, the properties of water changes from shallow to deep water. There are a lot of chemical underwater environment inside the sea, and there are different types of water. Could be one of them is pure sea water, where you have pure water and also some salt dissolved in it. You have clear ocean water, where you have high concentration of dissolved salts, and then you have coastal ocean water, where you have still higher concentration of dissolved salts, and then you have turbid harbor, where you have high concentration of dissolved salts and also suspended particles. So this is, if you want to communicate in turbid, it is very, very difficult because of suspended particles, a lot of scattering happening, a lot of absorption happening. So it's a challenge for communicating in turbid harbor kind of water. Optical properties, if I see, there are two types. One is inherent optical properties, which basically deals with the property of the medium only. That is how the optical beam is absorbed or scattered, or how it is affected, the propagation of the optical beam. So it deals only with the medium. It does not deal anything with the source. So that they are called as inherent optical properties, deals with the medium only, or in short, this is called as IOP. And the other one is apparent optical properties. It deals with both medium and source. So as I mentioned, medium basically tells how much light is absorbed, how much is scattered, what is the attenuation, and source, whether you are using a diffuse source or you are using a pointed source, or it also deals with the geometry of the source. So when you combine the medium and the source, they are called as apparent optical properties, and they are abbreviated as AOP. So what are the important factors that affect underwater optical communication? One, as I told you, is absorption scattering. The light is absorbed and also scattered depending on the type of water. If it has more suspended particles, then the light is likely to be scattered, and depending upon the impurity in the water, the light is absorbed. So this is one major factor which basically decides how much power you will get at the receiver. Turbulence, the water is not calm, so depending upon the turbulence, the receipt power intensity varies. So this is also going to be an important parameter that will affect underwater optical communication. Alignment, whether the optical transmitter and sources, they are aligned. If it is a point-to-point transmission, then we need to ensure the strict alignment between transmitter and receiver. We can also use some sort of, a diffused light. Suppose your receiver is there, probably that requirement of alignment can be relaxed here, because the beam width is quite high and the receiver will be able to send some amount of power. But there are issues with that, because you get less amount of power. The power is actually spread over a large area. So alignment is an issue. And multipath interference. In a point-to-point link, it is not necessary that you get all the light from the transmitter in straight path, that is line of sight. There is a possibility of light also coming from different other paths, getting reflected from the surface, for example. There is a surface. If there is some object somewhere here inside the water, this is an object, it may be reflected from here. So this might result into some sort of multipath interference, and you will have some sort of delay spread at the receiver, and that might introduce, ISI, the multipath interference is high, that is intersymbol interference. Physical obstruction. So if you have two transmitter receiver communicating, and suppose there is an interference here. It could be a rock, it could be some animal or some animal inside the some sea. So there may be a physical obstruction. Then you need to have some other node here, so the light will go like this, and then some processing might happen here, and then it is reflected back. This is how you avoid the obstacle. The other issue which we need to worry about is the background noise. So the background noise basically may come from solar radiations, which can go deep inside the water, and also the radiations which are black body radiations coming as a result of bioelements within the sea. That also is some sort of background noise for the receiver. So these are the factors which will affect the underwater optical communication systems. So we'll study these factors in detail now. So let us start with the absorption and scattering losses. So if I assume a small volume inside the water, which is something like this, so this is my input, that is pi lambda, and suppose this is delta V, which is perpendicular to the direction of propagation, and this is say delta R, which is in the same direction as the incident beam. If I consider this small volume of this delta V dimension, delta R dimension, and if I see across this, some of the light will be transmitted. This is transmitted part, and some of the light will be scattered. And say this angle is say psi, so this is scattered light. And this is transmitted light. And this is incident light. Let me denote this scattered light as Ps lambda and transmitted light as Pt lambda. So from the law of conservation, pi lambda, that is incident light, is sum of light, and some light will be absorbed inside this small volume of delta V and delta R. So this is a absorbed light. Absorption happens inside this. So this is absorption. And the light which is absorbed is say Pa lambda. So Pi lambda, incident light, is sum of absorption, scattered, and transmitted light. And if I defined a spectral absorbability, this is a spectral absorptivity. As the ratio of Pa lambda, that is the light which is absorbed, divided by the total incident light. And also let me define another factor, B lambda, which is spectral scattering. So let us write this here. This is spectral scattering, which is a ratio of light which is scattered divided by light which is incident. And the third one is spectral transmittance. So this is spectral transmittance, which is a ratio of light which is transmitted divided by the total incident light. And as you see here, sum of these parameters A lambda, B lambda and D lambda is equal to 1. Also define a parameter which is A lambda, and A lambda is actually spectral absorption coefficient. So let us define this as spectral absorption. This is how we will characterize the loss inside the water. Absorption coefficient. Which is a spectral absorption rate per unit distance. So this is as delta R tends to 0. I'm considering a very small volume or area, delta R. So as delta R tends to 0 and limit delta A lambda by delta R, where this is spectral absorption rate per unit distance. So this can be written as spectral absorption rate per unit distance. So this I am defining as spectral absorption coefficient per unit distance. And similarly, I am defining B lambda, which is spectral scattering coefficient. So this is spectral scattering coefficient, and this is equal to spectral scattering rate per unit distance. So this is how it is defined, limit delta R tending to 0, delta B lambda by delta R. So this is equivalent to spectral scattering rate per unit distance. Here we have combined these coefficients and A lambda, B lambda. The sum of this A lambda plus B lambda is C lambda. This is a combined coefficient which takes care of both absorption as well as scattering. And it has been shown, this is an approximate formula, how the light is attenuated inside the water is given by LP, which is a function of lambda, and the distance is exponential minus C lambda by Z, where C lambda is sum of these two coefficients, the absorption coefficient and the spectral scattering coefficient. There is A lambda plus B lambda. So this is exponential minus C lambda Z. So this is called as Beer-Lambert's law. And the values of A, B for clear ocean is, for example, 0.114 meter inverse, 0.037 meter inverse, and C will be simply addition of these two. Similarly, these are the values for coastal ocean, turbid harbor. As you see, the value of turbid harbor is very, very high because this is a water which has a lot of high concentration of dissolved salts and suspended particles. The attenuation coefficient is much higher as compared to clear ocean and coastal ocean. So now let us define another parameter which is called as scattering phase function. Scattering phase function, earlier we had defined one spectral scattering parameter, which was actually a ratio of scattered power divided by the incident power, which was B lambda. And now I define a function which is beta lambda psi. I'll explain what is this psi. So for example, you have a small area which is considered here as this. So this is say delta V, this was delta R, and this is incident light. So some light will be scattered, some will be transmitted. So this makes an angle psi here. So actually this is, I have drawn in a two-dimensional, but actually there is a cone around it, which is defined by this d omega. So I define a new parameter which I called as volume scattering function, VSF. This is volume scattering function. And this is defined as delta R tending to 0, this is tending to 0, and the solid angle is tending to 0, which is around this angle here. So delta omega tending to 0, so delta B lambda psi divided by delta R into delta omega is called as a volume scattering function. And if I find out the spectral scattering coefficient, this will be basically, I have to integrate over the total d omega, total solid angle, this volume scattering function. So this will give me a spectral scattering coefficient, and if I convert this d omega in terms of psi angle, then I get 2 pi 0 to 2 pi beta, that is a VSF or the volume scattering function, to sin psi d psi.